Everybody can hear me. I would like to introduce today's speaker, Henrik Winther, coming from the Masaryk University, Brno. It's a technical issue. Great. Who's visiting us for a few days from Brno, along with Mauro Mantegazza and Ian Flood. And he will be talking about non-commutative analogues of the jet functor for associated vectors. Okay.
Right. So this is together with Mauro and Keegan, as Ray said, at least those parts which are original to us. Actually, this idea started in 2019 in the Non-commutative black manifolds in Prague conference, where I talked to some people and I got the impression that the constructions we're about to discuss were possible in principle. And finally, this year, we set aside some time at weekly meetings and tried to make it happen. So I'm not an expert in non-commutative geometry, I'm a relative beginner. Some of the things that I say about that are probably going to be well known amongst the audience members than by me, but let's hope it works out anyway. But I'm going to try to tell you about the classical jet picture, which might be less well known to experts in non-commutative geometry. So what jets are, what structures they carry, and why they're useful. So this is going to be about vector bundles. And in the classical setting, we just got fiber bundles such that the typical fiber is a vector space, and you can add their sections fiber-wise. So that's also a vector space. And we will denote by gamma of pi, the space of sections of pi, although I'm not entirely consistent. Occasionally, I will write something like gamma of e when it's more convenient for the space of sections of pi. When you have vector bundles in classical geometry, you can always view them as principal bundles or associated to some principal bundles with a structure group H, which is a Lie group with a smooth action on something like a frame bundle. So these principal bundles mean that you have typical fibers, which are just diffeomorphic to the group with respect to its left action or right action on itself, depending on convention. And so it's free and transitive on the fibers, and the action is fiber-wise. So when you have such a principal bundle, you can take any H space for a structure group H, and you can construct an associated bundle by the construction that's up there. So the typical fiber of the bundle you construct like this is going to be diffeomorphic to the H space. It also inherits some structure, like if your H space is actually a linear representation or a module, then you're going to end up with a vector bundle. And in particular, this assignment takes you from vector bundles, E, to linear representations of H, which I will write as black or gold. So those two are associated with each other. So my first question, and actually this whole thing started because I asked Ray some questions over email, and he said, why don't you come have a seminar in Prague and tell us about what you're doing? Okay, but my principal goal here is still to ask you all about things that I don't know. I've asked Ray some questions yesterday.
This is the speaker, maybe just try and move it a bit closer to that.
Yeah, so this is the first question. Oh, no.
No, it's okay.
We are back. So my first question is that, well, actually define non-commutative principal bundles, but is there some way, given a non-commutative algebra A and a smooth calculus, to construct a natural principal bundle in the vein of the frame bundle in classical geometry? Because in classical geometry, you can always take a manifold, smooth manifold, take its tangent bundle, and this gives you the principal bundle of frames, which is a GLN bundle. So you end up with the natural structure group GLN for an n-dimensional manifold. So I wonder if there's some way to get a natural principal bundle structure for any algebra equipped with a smooth calculus. My feeling is that it's not possible, because if you did something like take the universal calculus, then you get something from nothing, and it seems unreasonable. But still, if there's some restricted class of algebras with extra structure, something where you can do this, I would like to know about it. Because that will make our constructions later more natural. Don't depend on some extra data. So there's going to be more questions in the talk, I'm afraid. All right, so let's start discussing jets. First of all, there are a lot of different notions of jets. If you have functions between manifolds, you can consider them their jets. If you have submanifolds in some manifold which are tangent up to some order at points, we call that contact to kth order, then you can consider jets of submanifolds. And if you have a smooth bundle, then you can consider jets of sections. It's the last version that we're going to be discussing today, although the other two are also very important. And maybe the middle one is more fundamental, but they are actually quite different. So we will be interested in jets of sections. And in particular, we are mainly interested in the case of vector bundles. So what is the jets of sections of a vector bundle at a point, or the jet space, as opposed to the jet bundle? Well, let k be some integer and take a point, x in n. Then there is an equivalence relation amongst the sections that all derivatives vanish up to, of their difference vanish up to some order k. So this is for written in terms of multi-indices. That just means that we take all possible combinations of partial derivatives up to that order. And if you have two sections that satisfy this, then you can consider them to be in an equivalence class. This is an equivalence relation section. And we have some notation for this. Yeah, at the bottom, the class of sigma of x is called jkx of sigma. And the set of equivalence classes of sections at x is called jkxi. So that's just at a point up until now. Depending on the structure of your vector bundle, there can be more explicit ways to write this, like in terms of algebra of smooth functions, for example. If that's your vector bundle, then you can write a much more explicit formula of this. So now we have a fiber over each point, but it's important that they also fit together smoothly to create a new bundle for us. Otherwise, we wouldn't have a jet functor on vector bundles. So if you take some bundle coordinates on some open subset in the total space of your bundle, then you add these new coordinates, which are related to the formal partial derivatives of sections, in the sense that they are evaluated, as I write in the second equation here. So you're just picking out partial derivatives of sections if you evaluate them on sections. And this gives you a smooth structure on the total space of the jet bundle. So that's also a smooth bundle on its own. And moreover, if the original bundle was a vector bundle, then this is a vector bundle. It's very good for us. We need to exploit that. So we have some geometric structures on the jet bundle, which will be important for us later. The first and most primitive one is like the universal differentiation, where we just map a section to its equivalence class in the K jet bundle. And that's just like a tautological thing, but it's also a kind of universal construction, so it turns out to be important. And in a non-commutative setting, we'll just have to compute it later. It's not that trivial there, at least in our example. Secondly, and more non-trivially, we have what's called a vector distribution on the total space, is the Cartan distribution. And basically, this means that if you take a path on the total space of the underlying bundle, then you can lift this with the universal differentiation operator. And you can consider like paths that are tangent to the prolongations of sections. And this generates a distribution for you. And if you want to see it in terms of the local coordinates we defined earlier, we can do that. It just looks like the formula for partial derivatives that you learn in multivariable calculus. Like if you divide by dx, let's say it's one variable, and you divide by dx, then it's just something like y prime is equal to dy by dx, right? And you can use that as kind of a mnemonic device to produce all these annihilators of the Cartan distribution. So you get this directly from the structure of partial differentiation. And this is the structure that actually remember in all your formal partial derivatives, what actual partial derivatives, or what was actually differentiated from something else. So that's the like, derivative relations encoded in the jet bundle. And what can we say about this Cartan distribution? Sorry, by the way, any questions about the Cartan distribution? Okay. So distributions can be really nice. In particular, they can be integrable, evolutive, and if you are in good settings, then these are all equivalent. Like, and its sections, like vector fields that take values in the distribution, are closed under the Lie bracket. That's just the definition of evolution. Or you can say that its annihilator is Frobenius integrable. That is the ideal generated in the exterior algebra is a differential ideal.
And so the ideal that's here is going to be due to the submap distribution.
Yeah. And finally, the one that's usually most important in classical geometry, if you have involutivity, then there exists an integral submanifold. So that's a submanifold such that this tangent space is equal to the distribution at every point of that submanifold. And for each point, you get a locally unique submanifold passing through it, and it just foliates your manifold. And these nice properties are not some properties that we have for the Cartan distribution. The Cartan distribution is in the opposite corner. It's something completely different that's called maximally non-holonomic, meaning that if you start taking Lie derivatives or Lie brackets of its sections, then in a finite number of steps, you will get the entire tangent bundle. But it turns out that that's actually not a bad property to have. Maximally non-holonomic distributions are very good geometric structures, classically. So let's discuss that. So one example is contact geometry, where you have a distribution that's of codimension 1 on an odd dimensional manifold. And it's totally non-holonomic, so you gain one more dimension when you take the Lie bracket. This has been a pretty successful geometrical structure. Like, you're probably familiar with symplectic structures, but it's like an odd dimensional analog, and in some senses, it's kind of more fundamental. And moreover, the prototype contact distribution is the one that comes from the first jet space of a scalar valued vector bundle. So there you have your Cartan distribution happens to be codimension 1. It's totally non-holonomic. So it's a contact distribution. The good part about these distributions is that they are flexible, meaning they have a lot of automorphisms, but they're not too flexible. What I mean by that is that if you have a diffeomorphism on the base, then that prolongs to a diffeomorphism of the total space of the jet bundle in a unique way. So there's no freedom there. And that's called the prolongation of the diffeomorphism. And actually, that is what turns the jet construction into a functor. So for any morphism, you have downstairs, you get a morphism upstairs. These morphisms are called Lie-Beckmann transformations. Or in the special case of first jets, they're called contact transformations, because that's actually the first case where contact structures appeared. And it's related to the terminology that I mentioned earlier about submanifolds which have contact at the kth order and so on. Kind of historical remark. Moreover, we have the same thing for infinitesimal diffeomorphisms, that is vector fields. Any vector field on the total space of the original bundle can be prolonged uniquely to a vector field that preserves the Cartan distribution on the total space of the jet bundle. That's called also the prolongation of vector fields. Any questions at this point? Okay. So let's say we are in the setting of a classical principal bundle. Then vector bundles are associated to modules, right? And when you construct a jet module, you get another, or a vector bundle, you get another vector bundle, which is associated with the same principal bundle. And so you get this nice commutative diagram of constructions. So what that allows us to do is consider, if you want, only the modules on the right-hand side here, and consider this to be an algebraic construction on modules instead of a geometric one in terms of like equivalence classes of sections and so on. And that's simpler to deal with in some sense. And it was this observation combined with the fact that in non-commutative geometry, they also have a notion of associated modules associated to representations that convinced me in 2019 that you could do something like what we're doing now.
Can you explain again this JK of E is somehow connected to the Berger module?
Yes. I'm sorry, I didn't have.
Yeah, you know what.
I can't go into details.
Yeah, sure.
It's something that I need to refresh in the future. It's a very good question.
It's also good because, of course, the Berger module makes sense in the quantum setting, so that's all good.
Yes. So finally, now we come to the applications of jet modules. So first of all, they allow you to formulate differential equations in a geometric way, and also to categorize differential equations. So you can talk about morphisms, categories. So a kth order partial differential equation is just a possibly nonlinear subbundle of the kth jet bundle, even if the kth jet bundle is a vector bundle. But if this differential equation is itself a vector bundle, then it's a linear differential equation. So you can talk about those Lie-Beckmann transformations, which preserve the equation. The special property that they have is that when you project them down to their original diffeomorphisms, they map solutions of the differential equation to solutions of the differential equation. So they're just acting on the solution space of the differential equation. And in fact, this action can give you a smooth structure of the space of solution. So you have a new manifold as well. And even geometric structures of this manifold. What's that?
There's a name for diffeo.
No,
That's the word.
This is not that.
It's not that.
That's more technical Vinogradov stuff.
Okay.
So anyway, we can also formulate what a solution is in these terms, and there are several ways to do it. One way is just to say that it's a section of the smaller bundle which prolongs into a section of the differential equation. Or you can say that it's a section which is tangent to the Carnot distribution restricted to or constrained to your equation. Now we come back to the universal differential operator, which we were discussing previously, because this jet bundle is actually the universal object for differential operators, which means that if you could define it in the non-commutative setting, then that would automatically define your differential operators as well. Well, you have some differential operators, but they don't, as far as I know, put together very well. So this would be a way to do that. And this is, universal objects are very nice, like, for example, tensor products are the universal object for bilinear operations. Jet bundles are the universal object for differential operations, differential operators. So anyway, any map between bundles which factors into one component, the universal differential operator, and then another component which we do not terribly care about is a differential operator. And here comes another question, which I'm also not terribly convinced will lead anywhere, but in the commutative setting, what I just said is equivalent to say that your differential operators commute with scalar functions up to some order. So scalar functions can be considered as operators on their own, they just multiply by themselves. And then you can take commutators between bundle maps. This is for maps from a bundle to itself. So you take k+1 arbitrary functions, and if this chain of commutators vanishes for all such functions, then you have a differential operator of order at most k. Could be lower as well, because k should be the smallest one that's allowed. And this, at first sight, looks really like it's global, it's algebraic. Shouldn't this be a good candidate for, like, if you could define this in a non-commutative setting, and then just say that, well, the jet bundle is the universal object corresponding to such operators. Boom, you're done. But actually, it doesn't seem to work that well, because your scalars aren't commutative anymore. So in particular, if you use this definition, then scalars are not zero order differential operators. It's clear that you have to replace the commutator by something that's inherently non-commutative, or deform this somehow, maybe in the deformation cases. And I don't know what that is. So I'd also like to pose the question to all of you. If you know what to do about commutator in a non-commutative case, please let me know. All right, finally, in non-commutative geometry, you also have connections. And in the classical setting, connections on a bundle is just equivalent to a splitting of the first jet exact sequence, which is this sequence. So if you know what jets are, then you also get another perspective for connections or covariant derivative operators. I don't want to say too much about this, except that that's also some property which I would hope to recover if this project goes well. Like, whatever our jet bundles are, they should have some relationship to non-commutative connections and covariant derivatives. Okay, now we come to the
okay, yeah, because I was a bit worried in the sense of, like, there's no proper definition of commutative differential operator, but what this is involving is actually connections of previous networks.
Yes.
Yeah.
Okay, so now we come to the non-commutative part of the talk, where I will first just establish some terminology, which hopefully is more or less the same one that you guys use, because we mostly got it from the book by Legs and Machine. So we have an algebra, and differential calculus is a bimodule algebra with a differential satisfying this Leibniz rule-like thing, and generated by its zeroth and first order component. And also, we will be using the universal calculus later, which is given by the kernel of the multiplication map in the tensor products with this algebraic derivative operator.
By the way, there's a message to Karen saying that there's a notion of acute forms actually related or something bracket. Could it be related to the non-commutative commutative?
Yeah, why not? I would like to take a look at that, but later. That doesn't sound not promising. So thanks, Karen. And thanks for keeping track of the chat. Right, so we're also going to need non-commutative principal bundles or optical and their associated bundles. So now we are in the setting where we have two algebras and a Hopf algebra. So A is just H is a Hopf algebra, P is any algebra, but it should be a right H comodule algebra. So we have the up map going from P to P times H. And then well, I'm mostly interested now in the case of universal principal bundles, so you can take these calculi to be the universal ones. If this is a short exact sequence, then it's a non-commutative principal bundle.
My general interest in this is equivalent to the Hopf-Galois extension.
Right, yes.
P is a Hopf-Galois extension. It's basically going there.
I was wondering how much you write. This is your topic.
Yeah. Trying to leave the audience in interest.
I see.
The audience.
Yeah, so if you have this structure, then you also have an association between A modules and H co-modules, which will be important to us. How am I doing on time?
I've got 25 minutes.
Right, another question for you guys. Suppose I have a associated module with some non-commutative principal bundle. That classically corresponds to the space of sections of a vector bundle. But the vector bundle also has a total space, which I can view as a manifold in its own right, put geometric structures on. And I would like to know if any of you know a way to go from the space of sections to an algebra corresponding to classically functions on the total space of this bundle. I feel like it should be possible to do this, but I haven't found anything so far. So please let me know if you know something about that. Was there a question there?
Yeah. It's something that should be well known. I've asked this question before. You get the answer. Yes, it should be well known, but I don't know what it is.
Okay. So what are we trying to do here? Let's think about what we want.
Sorry, there is a comment in the chat. Karen is saying if it's a line bundle, one can do it. But for higher ranks, she's not sure.
I would love to know that as well. Thank you, Karen.
We can discuss this later on.
Yes, unfortunately, I have to leave immediately after this talk.
Yeah.
But that sounds very promising to me. Right. So we're going to try to construct some jet bundles, and we have to think about what properties they should have. So for each vector bundle E, there should be an infinite series of A modules. That's vector bundles for us. E is also just a module now, which we can just name JKE. And such A modules already correspond to bundles over A, but jet bundles are actually not just bundles over the base space, they're bundles over each other. So you should be able to factor their projection maps so that you get like partial jet projections, go from JK to JK minus 1, for instance. And we should have definitely the universal differential operators going from the bundle downstairs, so space of sections of the bundle downstairs to the jet bundles for each jet bundle. And this should satisfy this relationship that if you first universally prolong something and then project it down again, you should get the identity, you just get back. Nothing should be forgotten there. And this is like the bare minimum that I could hope for. If you got something and it satisfies these first 4 points, I wouldn't quite call it a jet bundle yet because we're missing a lot. What would be really interesting is some notion of non-integrable distribution on there. And this relates back to the question about total spaces, because we can't put geometric structures on the total space if we don't know what the total space is. We're just stuck with the space of sections. So therefore we need to solve that. But the Cartan distribution must make an appearance for this to be a good generalization. There should be some relationship between splitting operators and covariant derivatives so that you can realize your old differential operators that you have from the covariant derivatives, their differentiation and so on, as some special case of the general differential operators coming from the jet bundle as delta factors through the universal differentiation operator. And in one particular case where E is A, so you're just thinking about the bundle of smooth functions acting on itself, there are some further relationships, like the first jet bundle is related to the cotangent bundle, and we would like to recover these things as well. Cotangent bundle in the non-commutative sense is just going to be the one graded piece of the smooth calculus for us. So we did something which we don't dare to call jet bundles yet. We call it the tower. And this is for universal calculi. So the maps that are going horizontally are constructions on objects. The maps that are going vertically are morphisms, so they can actually map elements in those objects to the other objects. And this can be simplified, but first let's talk about these vertical maps. Yeah, okay, if you have some assumptions, then you can simplify it to this, which looks much nicer. But the first version is a bit better for discussing the vertical maps.
So actually, just a comment, I was saying it yesterday as well. What you're doing is you're actually landing inside not only right H comodules, but also left P modules. So if your extension is what's the principal comodule that so it's Hofgawa and A is faithfully flat on the right and the left as B module would be the variance. Then by putting P on the left hand side, on the right hand side, sorry, on the left hand side of the category on the right hand side, then you get an equivalence of categories. This is Schneider's descent.
Right.
So that's extra information.
Right. We're not used to it.
And maybe it's something that would come in useful. That's just a comment. Yeah, sure. I appreciate all comments. I mainly came here to get help. So. So this is how to get the vertical maps. So you have this general homomorphism. Don't want to explain what the factor E is. It's not that complicated. It's from the Bex-Magid book. But in general, you have the top isomorphism. And if you pick your V and E carefully, you get the second isomorphism. What's interesting about the second isomorphism is that this is a map from a space to itself, and therefore it contains the identity map as a special morphism inside.
And then you can push that through to the other side, and you get a map from a space to another space, a different space, so it's not trivial anymore. And actually, that's what's giving the vertical maps in our tower. And it's similar for the last two equations there.
This is presumably some sort of natural isomorphism in the second.
Yes, it's a natural isomorphism.
Actually, what is C in practice?
It's a functor from Beck's sheet. If I remember right, it's not that complicated. It's a tensor product of P and take H invariant. Okay. Yeah, co-invariant. Yeah.
Probably a question here just saying, is there any relation between P and E beyond E being on that thing one of A? Or variance?
No, I don't think we used anything. So anyway, this looks a bit strange, but it's promising because we can calculate it more carefully in a particular case. And that case is for the E equal to A. So just considering the smooth functions over themselves. Then we get some more properties. So you can start with the trivial representation if you want, just to make it even more similar to the classical case. And then if you start with the trivial representation, the associated module is the space of functions. Okay, that's A for us. And then you keep going down the tower, and you come to P times P as a co-invariant H, which is something new. And that's our candidate first jet space for A. And so this is in the universal smooth calculus. That is the kernel of the multiplication map in A tensor A. Now A is the co-invariance in P. So of course A tensor A includes into P times P co-invariant H. And so actually in this picture you have the cotangent bundle included into the first jet bundle. And now we can chase through the homomorphisms that we were using on the previous slide and calculate that the projection map from P times PH to A is just a multiplication map in the case of the universal calculus. So now that we know that, we can solve for the bundle map that gives us this property that you go up and go down again and it's the identity, and it shows up your bundle map. And it gives us that the universal differential operator of some element A of A is just A times 1. Okay, that's actually also really promising because if you skew symmetrize this, you get one component which is just the exterior derivative, which precisely matches your expectation coming from the classical picture. It should be the exterior derivative plus some extra component. And that's basically the only reason I think this notion of the tower is reasonable at all, but it fits a lot more slots on the list of desirable properties. It's necessarily needed to. So now we have a problem. We have a tower of bundles, but actually it doesn't look anything like the tower of jet bundles, even though we have the jet projections. What it does look like is iterated one-jets. And in classical geometry, iterated one-jets can be used for some properties. Like in parabolic geometry, you can do it with just iterated one-jets without proper two-jets. But for stuff like partial differential equations, it's just not enough. So you cannot get a reasonable theory of non-commutative PDEs of higher order using just what I described earlier. It's likely that it's related because iterated one-jets are related to two-jets and higher jets, but it's not the same. Are there any comments to the more comments? Okay. So anyway, we need to figure out how the tower relates to actual higher jets rather than iterated one-jets. Now about the Cartan distribution. I have another question for you guys. Did anybody in the non-commutative geometry consider like vector distributions or non-holonomic vector distributions in particular, or even integrable vector distributions? If so, I would like to know about it, because we're going to have to introduce the generalization of the Cartan distribution. If not, here is the start of our attempt. So we have,
as a comment, I think you're safe enough. I have never heard of any considering such a.
Okay. Yeah, so we had three good points of view for vector distributions earlier. We're going to take the differential system point of view here. And that means we're going to have to take some ideal in the calculus of some space, probably the total space of the jet bundle in my application. And this should be a graded ideal and generated by its first order component. You should have this, it should be two-sided, and you should have this exact sequence. Yeah. If this happens to be a differential graded ideal, then we call it the Frobenius system, and that's basically our guess at what integrability looks like. But of course, we are not expecting integrability for the generalized Cartan distribution.
In the classical case, this idea is not like subvector one.
Yes, it is a
subvector one. And like if you're on a homogeneous space, for example, where the one your algebra, your Dirac complex is going to be composed of homogeneous vector. Will this thing then be a sub-homogeneous vector?
If it's invariant with respect to the structure group or the isotropy group, then it should be.
So there are examples where. Yeah.
Anything else? Okay, so to torture ourselves a little bit, we also wanted to think about something that sounds hopeless. Because classically the most important part of integrable distributions is this submanifolds, but that definition starts with through every point of M, there passes a submanifold, blah, blah, blah. And we already have issues with the first part of that definition, through every point of M. We don't have any points of M in general. Points of M classically are just evaluation maps that go to your algebra of smooth functions, mod some maximal ideal. We started thinking that maybe it's possible to do something by replacing these evaluation maps with more general evaluation maps, where instead of fields, you take different algebras R and homomorphisms. But I think even this is probably too strong to demand for general non-commutative algebra. So we'll not have. I don't think it will work if you take something like simple algebras R here. Probably won't have any points in general anyway. So I would like to know if anybody has tried to see what this sort of generalized points, maybe using a different idea than what we're doing. I know you don't like points, but for the purposes of integrable submanifolds and foliations, it would be nice to say something. Not that I'm that hopeful.
I feel like Q to 1 plus 1 bracket also gives a notion of a non-commutative foliation.
Very good. Yeah, that's promising.
So this is what we were talking about earlier on, basically, these foliations. Very good comment, Karen.
Thank you, Karen. You're very helpful to me. Okay. And finally, here's a list of challenges composed from mostly from my questions during this talk about which steps we would need to take to define properly geometric non-commutative partial differential equations. So first, we need to go from sections to total spaces in order to introduce geometric structures directly on the jet bundles. Karen said that there might be some hope for that, so that's good. We need to understand non-commutative distributions and hopefully find the Cartan distributions. Well, if we have the space where it lives, then at least that's partially solved because we only have to see how it's induced by the universal differential operators that we already have. And so on. So maybe that's also possible. We need to figure out what higher order jets are because all the interesting differential equations in physics and so on are second order and above. Yeah, needs some thinking on our part probably. And finally, maybe most importantly, we need to generalize the whole construction from universal calculi to general calculi, because for now, this is just for toy examples. I don't think you will get anything particularly interesting because there's basically no geometric information in the universal calculus, just playing with tensor products. But once we finish these steps, then we should be in a good position to formulate the geometric non-commutative PDEs. So I think that's the final slide. Thank you for listening.
Okay, so we have questions from the audience or questions from the audience online. If there's not, I'll start with the comments. I mean, it's very much early days, but it looks very promising. Yeah, so some directions promising, I guess, but we've discussed which ideas I think are. But
I don't think this has been a bit of a scattershot.
Yeah,
I don't think all of these approaches are good.
Yeah, I mean, this is what happens when you start to know something new in its early days. It's exactly what, but no, it's certainly very interesting. My advice would be to ground everything in examples because they will help you guys to go where you're going.
Good comment.
Although Branimir has a question, but I'm just going to, maybe I'm going to make a comment and ask Karen a question at the end. So I think what you're saying, Karen, about the line bundles, you're looking at some Kunz-Pimsner construction, basically. Yeah, Karen says yes. So yeah, this is what I should have remembered, but I didn't basically. So I'll explain, Karen, if you don't mind. You don't have any audio. When you take the line bundle, when you tensor out of the line bundle, that gives you the total space. That gives you the functions on total space.
I see. Yeah, that's reasonable.
Yeah, which if you look back to the usual example, CP1, if you take the first topological line bundle of this, and then you take tensor out, what you're going to get is, yeah, but this is how it works. You're checking the Kunz-Pimsner out. So yeah, we can talk about that. This is what then it works for line bundles, but I mean it's certainly.
Like I said, scalar valued PDEs are living in line bundles, like and scalar valued PDEs, especially at higher orders, are already extremely interesting. Also, this is where you get the prototype contact structures and stuff like that. So it's not a bad place to start.
Yeah. No, so it's something you should have remembered, but I've forgotten. They're also meant to use for purely C-star algebraic point of view. There's something that's very exact. All related, but you have that one too as well. So, but thanks, Karen, for reminding me of that, which I forgot. Now, Branimir, you have a question?
Yeah, I think well, the one thing is I would wholeheartedly guarantee, sorry, good Lord, I can't speak today. I would strongly agree with the suggestion of really looking at quantum circle bundles, like looking at line bundles. There's this nice Kunz-Pimsner situation going on there. There's already a lot that can be worked out there that would be very instructive. The actual question, though, that I wanted to ask was this choice of quantum principal bundle P over A. I mean, what is the significance of this choice? Because a given A
that's related to. Sorry, I didn't mean to cut you off.
No, it's all good. All good.
That's related to the first question in my talk. Is there a natural way to choose the structure Hopf algebra and the quantum principal bundle? Because if we had that, then that construction would be natural. As for now, you are picking extra data. And even though we are producing the cotangent bundle in our example of the functions, this should not depend on the principal bundle. This should depend on nothing. So there's a bit of an unnatural dependence on P at the moment.
So I mean, geometrically, like, what does the choice of this datum represent?
It's totally unnecessary classically, so I don't know.
I mean, maybe you could get some mileage. This is a story that Ray knows far better than I do, but you might even be able to think about non-universal things if you consider the case of frame geometry. So you have situations where your one forms on A are actually an associated vector bundle to some quantum or principal bundle over A. And so this might be a nice situation. And this might be a nice situation to deal with. Another nice thing there is that then you have I feel like there's a lot that you could do without necessarily having a total differential calculus on P. You might be able to get away with just having a notion of horizontal forms on P to a certain extent, in which case there's a canonical candidate. I mean, if you're framed, then there's a canonical candidate for what the horizontal one in the forms upstairs ought to be, or at least the one forms ought to be. So I suspect that the frame situation might be worth looking at in particular too. And some of the more interesting examples fall into this regime, like everyone's favorite, the theta or acutiform complex Hopf vibration. Well, with the sort of natural differential calculi, will fall into this sort of regime.
All right. Yeah, I hope this is recorded and I'll listen to it again when I get home. Thanks,
yeah, it'll be put up on the YouTube channel so you can get it right.
Good.
So, Bishop, a stupid question is always on that. Could you spell out the difference between iterated one jet and higher order jets?
Yeah, because you're only taking derivatives when you do higher order jets. You're only taking derivatives with respect to the base variables. But when you're taking iterated one jets, you're also taking derivatives with respect to S prime, for instance, which is kind of a natural thing to do from the higher jets perspective. So if we're doing two jets, you would get jets like, let's say you are in the scalar value of one independent variable case. Then for the first jet bundle, you would get X, S, and S prime as your variables. Okay, so now you want to go to either iterated one jets or two jets. If you want to go to two jets, then your coordinates will be X, S, S prime, and S double prime, because you're only differentiating twice by X. On the other hand, if you are going to iterated one jets, then you have to consider this whole thing as your free variables. So you have to differentiate S prime by S prime, for instance, or S by S prime, and other things like that. So it's a much bigger space with much less structure on it. I hope that was clear. If not, I'm going to have to write on the board.
Yep, bad vision says thanks. Okay, so do we have any more questions either online or in the audience? No, it doesn't seem to be. So yeah, it seems like you've got trying to Brno, you're on schedule, so you should make it. So in that case, I would thank you again for a very nice talk, and yeah, let's see what happens. And I guess I should announce next week's talk. Can somebody